Hi everyone, I am Misiki. Today I'm going to introduce you all to the topic of magnetostatic and how to use the Biot-Savart's law to calculate the magnetic field intensity. Okay, so for the second chapter is about magnetostatic. So for the first chapter, we have learned the electrostatic. Okay, so second chapter we learn about the magnetostatic. So for the electrostatic, we are dealing with electrons, right? Static electrons. What kind of what is the electric field intensity and what is the source? What is the force between the electric electron? Okay, we have learned how to calculate it. All right, so for this chapter, we are going to deal with the magnetostatic, okay, magnetic field and static magnetic field in this chapter. Right. All right. So what can you think about when we talk about magnet? Okay, maybe you can magnet. I mean, you can imagine there is a magnet bar. Okay, so this is the north pole and this is the south pole, right? Magnet bar, and these are the magnetic fields around this south pole and also the north pole of a magnet bar. So if you spread the iron powder around this magnet, so you will be able to see this magnetic field line, okay, in between stems. I think we have tried this before, maybe in our secondary school or in maybe in your polytechnic. Okay, we have tried this before, right? Okay, so the source of the magnetic field is not just restricted to the magnet bar actually. Okay, so the magnetic field is actually produced, okay, by permanent magnets, okay, like I said just now, and steady electric currents, and as illustrated in the figure below. So when you have a conductors and a current flow, okay, you actually it will generate the magnetic fields around the current element. Okay, so if you bend your current element in the form of solenoid, so this is how the magnetic field, okay, oriented, okay, in between the north pole and also the south pole when you bend your wires, okay, in the form of solenoids. So magnetic field can be generated by permanent magnet and also wires when there is current flowing in the wires. Okay, so beside that, okay, you can also bend your wire in the form of a loop of wire. Okay, so this one will be the directions of the magnetic field, okay, that is surrounded your loop of wire. And actually our earth itself is also a magnet. Okay, it's also a magnet, right? So when you use the compass, you will see that the compass is pointing in the south and also the north pole directions. Okay, this is how we determine the directions, right? So our earth itself is also a magnet. Okay, so electrostatic field is produced by static stationary charges. Okay, this is what we learned in the chapter 1. So for this chapter, the magnetostatic field or the static magnetic field is produced by a constant current flow or direct current, DC current. So when you have a current flow, you have static magnetic field. Okay, so the current may be due to the magnetization currents as in a permanent magnet, okay, and also the electron beam current as in the vacuum tubes, and the conduction current as in the current carrying wires, okay, which I explained just now. So in this chapter, we are going to learn two law that actually help us to calculate the magnetic field, okay, from the current element. The first one is the Biot-Savart's law. The second one is the Ampere's law. So these two, they are actually quite similar to the Coulomb's law and also the Gauss law in the first chapter. Okay, but this one, Biot-Savart and also the Ampere's law, it is applied for the magnetostatic field. Okay, so we will going to look at it later. So let's actually look at the attributes of the electrostatic and also the magnetostatic. Okay, so in the first chapter, we learn about the electrostatic. So it is actually produced by the stationary charges, proton, electron, right? And for the magnetostatic, it is actually produced by the steady currents. When you have a DC current flow in the wires, then it generates the magnetic field, all right? Okay, so the terms, okay, that we are dealing with in this magnetostatic is the H and B. So H stands for the magnetic field intensity and B stands for the magnetic flux density. Okay, quite similar to this one. This is the electric field density. This is the electric flux density. Right. Okay. So for the constitutive parameters, okay, that describe, okay, the mediums. Okay. For the electrostatic, we have used the epsilon. Okay, epsilon, and this is conductivity when you are dealing with the material that has the loss factors. Okay, but we don't dealing too much with this kind of material in our first chapter. We're just dealing with the material that has the dielectric constant in our first chapter, right? So we'll be dealing with the epsilon, okay, for the electrostatic. So for the magnetostatic, we'll be dealing with the mu, MIU, mu. Okay, so this describes the magnetic properties of the material. Okay, so these are the law that we have learned before in the first chapter, right? Okay, so these are the equations in the differential form and in the integral form. And this is what we are going to explore in this chapter. Okay, and also the potentials, okay, the energy density, okay, the force on the charge. Okay, this is what we have learned. Okay, and in this chapter, we are going to learn this one. Okay, right. So for the permanent magnet, such as the bar magnet, so it has a magnetic field surround it that consists of line of force or flux line. So this is what I explained to you before. So if you put a magnet bar and you spread the iron powder surround it, then this is the view that you can see. Okay, so the iron fillings that actually they will arrange the cell according to the flux line. Okay, the magnetic flux line. That's why you see a line, something like this. Or if you're putting a compass, okay, surround or at the edge of the magnet bar, you'll be able to see that this compass it will be deflected according to the directions. Okay, so the magnetic field will actually originate from the north pole and terminate at the south pole. That's why you see this one is something like it going out and this one is going in. Okay, so the directions of this compass actually can help you to determine which one is the north pole, which one is the south pole. Okay, so for the North Pole, if they are simultaneous, okay, they will repel each other. If they are both South Pole, they will also repel each other. Okay, they will repel each other. And if they are in opposite poles, they will attract each other. I think this one you know well, right? Okay, so for the magnetic field, it is characterized by the B and also the H vector. Okay, so both are related by the permeability or the magnetic constants, okay, mu of the mediums. Okay, so this is the parameter that actually linking the B and also the H. So what is the H? H, we call it as the magnetic field intensity or the magnetic field strength. Okay, so the unit of this H is amperes per meter. While for the B, okay, it is known as the magnetic flux density. Okay, magnetic flux density. So, or you can call it as a magnetic inductions or magnetic field. Okay, so the B has the unit of Tesla, T. Normally we use it T. Okay, equivalent to Webers per square meters. Okay, so normally we will use a T to represent the B. Okay, the magnetic flux density. Okay, so let's look at the Biot-Savart's law. Okay, Biot-Savart's law. So what is the purpose of this law and how to use this law? Right. So just now I briefly talked to you all that this law is mainly for us to use to calculate the magnetic field intensity at a point. Yeah? So what the Biot-Savart's law says? So the Biot-Savart's law states that the differential magnetic field intensity, okay, DH, DH. So differential magnetic field intensity is a DH, produced at the point P. You can look at this figure. Okay, the H produced at the point P, okay, by the differential current element IDL. Okay, you imagine you have a very small current element, okay, IDL is proportional to the product IDL and the sine of the angle alpha between the elements and the line joining P to the elements and is inversely proportional to the square of the distance r between the P and the elements. So basically, this sentence explains these equations. Okay, explain these equations. So the differential magnetic field intensity is proportional. Proportional means that when this increase, okay, this DH, differential magnetic field intensity, will also increase. Okay, so this IDL represent the length, okay, the smallest length, okay, of the current element, and the I represent the the currents in these small elements, okay, in these small wire elements. Sine alpha, alpha is the angle, okay, you can see here, this is the angle that actually join in between the DL line and also the line joining the observation point P, okay, joining the observation point P, yeah, okay, the angle. So if you rewrite this one, it will become IDL cross unit vector R. Okay, unit vector R. Okay, so this one, unit vector R, actually describe the directions of the magnetic field. While this one can be changed to this one, if you remember, okay, if you remember the cross product between the, where's my pen? Okay, the cross product for between one vector and also the other vector, it will be equals to the magnitude of the vector, okay, multiply with the sine theta, okay, between terms. Okay, so sine theta, the angles between the vector A and vector B. So in this case, our vector A will be this one, okay, DDL, and the vector B is the R. Okay, so this thing, if you rewrite it, it will be this one over this, right? The magnitude. Okay, the magnitude. Okay, so if we write this thing, so here will become power 3. Okay, power 3. Yeah? So this is the relationship, okay? Okay, for the cross product for two vectors. Right. So this is just the magnetic field contributed by this very small element. And imagine your current element, okay, is so long. Okay, so the total magnetic field, okay, observed at the point P will be equals to, you integrate this one, okay, you integrate this one with respect to the length. Okay, this one is representing the length, okay, the length of the current element, okay, of the current elements. Okay, this one should be power 3. Um, yeah, this one should be power 3. Yeah, should be power 3. Okay, should be power 3. All right. Okay, so I think you observe right here there is a cross. It's a symbol, something like this. Cross, something like this. So you will observe this symbol a lot in this chapter. Okay, so this actually means that the directions of the magnetic field. Okay, if it is in this symbol, it means that the electric field, the magnetic field is in. In means it going into the page. Going into the page. If it is in this shape, okay, is this symbol, so it means that the electric field, the magnetic field is going out from the page. Okay, going out from the page. Okay, just like when you are sewing you're using the needle for sewing. Okay, okay. So if your needle is going down and up, then so it will be in this symbol. If it is going in, it will be in this symbol. Okay, showing the magnetic field is going in and this one is going out, outward. Okay, so the directions of the magnetic field, we can determine it easily by using the right hand rule. Okay, so for this rule, okay, you will use your right hand. Okay, this is your thumb and this is the fingers, the other four fingers. So the thumb will shows the directions of the current flowing, and the direction of the other four fingers will show the directions of the magnetic field. Okay, so you can easily determine the directions of the magnetic field. For example, just like this case. So if the current is flowing in these directions, okay, you can use your thumb, okay, showing your directions is flowing this way. So the other four fingers will be going in this way. Okay, will be going in this way. So as the result, okay, You can imagine. So the magnetic, this is the directions of your other four fingers, right? So for at this point, the magnetic field will be going into, right? Going into, see, going into. Okay, so that's why they use this symbol to represent the magnetic field directions at this position P. Okay, so you can also use the right-handed screw rules. Okay, basically they are still the same lah. Okay, so this one shows the magnetic field directions. Okay, this is the current directions. Okay, I think this one will be easier for you to imagine lah for the using the right hand rules. So for the magnetic field, it can be generated by different kind of current distribution, just like in the magnetostatic chapters. Okay, you can generate electric field intensity due to the point charge. Okay, a line charge, surface charge. Okay, as well as this one. Okay, so for the magnetic field, it can be generated by using different kind of current distribution, such as the line currents. Okay, when you have a line and your current flow in the line, then you can generate the magnetic field. Okay, and for when there are many currents, okay, on the surface of a plane, okay, it generates the magnetic field as well. Okay, so this one is from the surface currents, surface current. Where K is the surface current density. Okay, this is the surface current density. This one is the current I, current itself. Okay, that passing through the wires. So this is the surface current density. And for the volumes, okay, so okay, you will be using the volume current density, okay, to find the magnetic field, okay, inside a volume of structure, okay, inside a volume of structures. Okay, so this one is about the derivations, how you come up with the final equations to calculate the magnetic field at the point, okay, due to the current elements. Okay, so I will explain this one. So this is your current elements. This is your current elements. Okay, so imagine you have a currents, okay, flow in these directions, okay, flow in the z directions. Okay, so this is your observation point, point P, that you wish to find the magnetic field. Okay, so you join these two lines, okay, you join this point B and also the point A, okay, with the observation point P, observation point P, which is very similar to the equation, to the electric field intensity that we calculate in chapter 1. Okay, you need to join it, and this alpha 1, okay, will be with the point A. Point A normally will have smaller value, point B will have a larger value, and this alpha 2 is with the point B. Okay, joining them. Okay, so this alpha 2 and alpha 1, you can easily find it, okay, when you join the lines, okay, when you join the ends of the current elements with the point P. Okay, R will represent the distance. If you remember, okay, last chapter, okay, we have to find out where is the point T. Okay, what is the coordinate of point T? So this coordinate point T is important for us to find the R, the distance, okay, between the point T and also the observation point, point P. Okay, while this phi, okay, represent the directions of the magnetic field. Okay, so these directions of the magnetic field is equals to the cross product of the direction of the current. Okay, for example, this one is the direction of the current. It is pointing in the z directions, z directions. Okay, and the direction of the r. Okay, so this r is pointing in the x directions, pointing in the x directions. When the z cross product with the x, okay, you will be able to get x, y, z. Z, will be able to get y. So your magnetic field will be in the y directions. Okay, how I get this thing? Okay, you can refer to the formula. Sorry, the formula that I shared with you before. Okay, you can look at this one. This is the formula that I shared with you before. Okay, so this is how you get this. Okay, when the z cross product with the x, you will get vector y. Okay, or you have the other way to actually to determine the directions of this y. Okay, let me show you. Okay, so you arrange. You need to arrange. Okay, you arrange your X here. Okay, your Y here. This is the directions, and Z here. And you put in the arrow in between them. This is how you determine the directions. If the X cross product with the Y, X cross product with the Y, you are following the directions of the arrow, so you will get positive Z. Okay, so for this one, you see Z cross product with the X, Z cross product with the X, you will be able to get Y. Okay, but if you are inverse or if you are in the opposite directions of the arrows, for example, Z cross product with the Y, okay, you are in the other directions, right? So it will give you negative X. Yeah, it will give you negative X. Or sometimes you might find that you have to cross product negative X plus, plus X. Cross product with, for example, X. So Z cross product with the X, supposedly you will get Y, but because of this negative, you will get negative Y. So this is how you determine the directions of the magnetic field. Okay, so by putting all the elements alpha 1, alpha 2, R, I normally it will be given, and this is the directions of the magnetic field. You will be able to calculate the magnetic field intensity, which is from a finite current filament. Finite current filaments. Okay, we will look at the one of the examples in the module. So you can read through all the paragraph in the module. Okay, so this is what I have explained previously, and this is the Biot-Savart's law, right? Biot-Savart's law. Okay, so here it already explained how this thing, okay, can be involved into here. Can be involved into here. So I already explained. Okay, so this one should be power 3. Okay, so this is the directions of the magnetic field. Magnetic field is into the page, and this is out of the page. Right, so this is the directions. So everything same like the PowerPoint. So we look at this one, example 2.1 of your module. You can turn to page 106. Okay, so it is a given straight current filament as shown in the figure 2.5. Okay, so you have to derive the magnetic field of this current filament. So in this first one, okay, it actually show you the steps to derive the equations, okay, as in here. Okay, same thing. Basically same thing. You can look at it. Same thing. Okay, so they start from here. Okay, we always start from here. Okay, so if you look at this example, current is flowing in the z directions. Okay, z axis. This is the z axis. So current flows in the z directions. Okay, currents flow in the z direction. So your dl is the length of your current filaments. Okay, it is following the z directions. So it will become dz, positive z. Okay, so this positive z direction shows that the current is flowing in the positive z directions, and following the length in the z axis. All right. So R is the distant vectors. Okay, distant vectors between the observation point P and the current filaments. Okay, distant vectors. Distant vectors. Since the coordinate along the current filaments are 0, 0, z. Okay, why 0, 0, z? Okay, so this is your current filaments. Your x coordinate and y coordinate are both 0. But for the z coordinate, okay, it is depend on the length of your current filaments. Okay, that's why it is 0, 0, z. It means that the z can be any value. Okay, so in order to find the distant vectors, okay, distant vector will be the observation point minus the source point. Okay, so this is the this is a position vector of the current filament, this one, right? And this one is the observation point. Okay, you look at observation point. Okay, the coordinate of this observation point is 0, r, 0. The length over here is r. Okay, so that's why you come up with this thing. Okay, and this is the distance vectors, and this is the magnitude of the distance vector. Okay, so when we put this one together, dl cross with the r, where is this? This one. dl cross with the vector r, okay, you'll be getting this one. Okay, you'll be getting this one. r dz phi. Okay, r dz phi. Okay, and the phi is equals to this one. Phi equals to this one, like what is told over here. dl cross with the r. Okay, dl cross with the r. So when you put in all these things inside, you will get this thing. Okay, so this is also another formula for you to calculate the magnetic field. So you have actually two choice to calculate, two formula that you can use to calculate the magnetic field. The first one is you use this thing. Okay, this thing they already simplified for you. Okay, you don't need to go through the integration process anymore. You just need to find out what is the alpha 2, what is the alpha 1, and what is the r. Then you replace into it, then you can get the equations. Then you can get the answer. The other is you go through by using the integrations. Later I will show you both steps. Okay, I will show you both steps and you can see that you will get the same answer. So this one, of course, it will be easier if you use the calculator. Okay, if you use the calculator, sorry, if you use the software to help you to calculate. Okay, you just insert everything, then the software can automatically calculate for you. Okay, so this one is about the simplifications, okay, of these equations. Okay, and finally you come up with this cos and also the cos alpha 2 and cos alpha 1. Okay, so for this equation 2.8, it is applicable to all straight filament conductor of finite length. Okay, remember this one is finite length. Okay, so it can lie in any axis as long as it is a straight line. Okay, finite length and also a straight line. Yeah. Okay, so this is about the derivations for this one. Okay, so now you have to calculate the magnetic field H when the I is 5 ampere, P is this one, okay, and A is this, B is this. Okay, so we have to replace the value into it. Replace the value into it. All right, never mind. Let me snap this one. Let's snap this one. I'm going to show you how to get the answer for these questions by using different technique. So the first one is we use the formula. Okay, you use the formula. So this is the formulas. So the formula given is this I over 4 pi r, right? Cos alpha 2 minus cos alpha 1 and this. Is that correct? It's correct, this one. So let's draw these current filaments. So it is located here. 2. This is 2. This is y-axis. This is 2. This is the x-axis. Okay, so your current filament is along the z-axis and the I is 5 ampere from 1 to 6. From 1 to 6. So this is your current filaments. Current flow in these directions. This is 6, this is 1. Right, 6 and 1. So now you want to find the magnetic field at this position using this formula. Okay, so the first step is we joining the line together. Okay, we join the line together. So we join the line together. Okay, join the line together. Okay, and label your alpha 1 and also alpha 2. So this is point B, sorry, because it has larger value. And this is point A because it has smaller value. So this one will be your alpha 1. Okay, you can check. This one will be alpha 1. And this one will be your alpha 2. Okay, so you roughly know what is your alpha 1, alpha 2. Now we move on to the R. Okay, to find the R, okay, we have to find this thing, okay, distance vector R. So you have to extend your line, okay, just like in the first chapter, you extend your line, okay, then you joining this extended line with the observation point here. So this is the point T, your point T. So your observation point has a coordinate 0, 2, and 0, right? So for this point T, okay, point T, okay, the coordinate of point T will be following the coordinate of the line, which has the x0, right? And your y is also 0, right? Y is also 0, huh? And the z value, you have to follow the z value of your observation point, which is 0. Then only you will get a 90 degrees over here. I think I told you before, right? Okay, how to determine the point T over here. So for this thing, okay, it will be equals to, you take this, the distance vector, sorry, the position vector of the observation point, 0, 2, 0. This one we call it as the position vector because you see this is a symbol of the vectors, okay, minus the position vector of the point T. Okay, so you know that it will be equals to 0, 2, 0. Okay, this one is for your vector r. So you can calculate the magnitude of this r easily, which is equals to 2. Okay, which is equals to 2. So this symbol, okay, represent the magnetic of the vector r. Okay, so you have got this thing, right? So in fact, your question already give you this one also. Okay, I already give you this one. So now we move on to this one. Okay, what is this? This is the directions of the magnetic field, and it is equals to the directions of the current filament cross product with the distance vector. Okay, between the observation point and also the point T. Also the point T. So this one will be looking at the directions of the current filament. Okay, so if your current flow in the z directions, okay, this one will be z. And cross product with the r. What is r? So just now we already calculate these two things, right? So we can continue to calculate it. To get our unit vector r. Okay, so this is 0, 2, 0, right? And you divide with the 2. Okay, so you only have the y component, which is 1y. Y component. So this one will be y. Okay, so we will arrange our vector in these directions. Okay, then we will know what is the cross product for the zy. Okay, so this is the directions of the arrow. Okay, now z cross product with the y. Z cross product with the y. Okay, you are in the reverse directions of the arrow. So this will be negative x. Okay, you move and you will get x. But because you move in different directions, so it is negative x. Negative x. So now you have got everything ready. Okay, you can put them into your equations. Okay, this is your equations. Oh no, not yet. Not yet. We have to find out what is the alpha 1 and also the alpha 2, right? And alpha 1 and also the alpha 2. Let's look at alpha 1. Okay, alpha 1. You look at this triangle, all right? Look at this triangle. So I'm going to draw it here. The alpha 1, this is your alpha 1. And this is your point P, right? Point P. And this is your point T, right? 90 degrees. This is your alpha 1. Eh? And this is your R. Just now we already calculated it. The length is 2. And from point T to this point, okay, this is point A. The coordinate is 1. So obviously here you will have a 1. Okay, 1. So what is alpha 1? Okay, you can use a tangent. Tangent alpha 1 will be equals to opposite over adjacent. Opposite over adjacent. So it will be equals to, you can take your calculator. Where's my calculator? Okay, so you have to, if you want the angle unit to be degree, you can change it to degree. Okay, so the alpha 1 will be 63.43. Okay, this is your alpha 1. Look at the alpha 2. Where is alpha 2? You see alpha 2? We have to form a triangle. So I will going to draw this triangle. Okay, I'm going to draw this triangle for my alpha 2. This is point P, this is point T, and this the length over here is 2 unit, right? And from here up to point B, the coordinate is 6. So here you have a length of 6. Okay, this is your alpha 2. Okay, alpha 2. So again, you can use a tangent, alpha 2, to find the angle. Okay, opposite over adjacent. So your alpha 2 could be 18.43. Okay, 18.43. So now you can replace it here. I want you to replace yourself. So this is the formula for the magnetic field, 4 pi r. So you have a cos alpha 2 minus cos alpha 1. And this is the phi, alpha 2, alpha 1. Okay, so the magnitude of the current has been given, which is 5 ampere. Okay, 5 ampere. Divide 4 pi. Okay, the length, the magnitude of the R is equals to 2. So your cos alpha 2 is cos 18.43. Okay, minus cos 63.43. And this, you already calculate it just now, which is negative x. Okay, negative x. So you can start calculate. So you get 0.099, almost 0.1, 997. Okay, negative x. Amperes per meter is the unit. Is it the same answer? Okay, the same answer. It is in the x directions. So the direction missed out. Okay, should be negative x. It's up to you whether you want to use the tangent to find the angles, or you want to use the trigonometry straight away to get this thing for your angle. Okay, in the end you will still get that same answer. You will still get the same answer. This one. Can you understand the flaw to calculate the magnetic field intensity? The H. Anyone has problem to understand this? Okay, so this is method one. Okay, thank you for the response, Mikli. Okay, so this is method one. Okay, method one, where you apply the formulas. This one. Then you apply the formula. What if you don't want to use this one? Okay, you use this thing, which is based on the integrations. Okay, what you should do? What you should do? Okay, so for this one, right? So you can refer back here. So what is the equation that we are going to use? So we should actually start from here. Okay, we should actually start from here. Right, we should actually start from here. Yeah, start from here. Equations, this one. Let's see how we can do it. So this is method 2. Method 2. So this is h equals to, you integrate IR dz over 4 pi r square plus z square power 3 over 2, and this one phi. Okay, so for the phi, you still have to use the method that I explained just now, where you cross product, okay, the directions of the length with the directions of this, okay, which is the z. Okay, you cross product with the y. So you get negative x. Okay, this thing you still have to use this method to get the directions. But for this one, okay, you can put the value into it. So for the length of this current filament, okay, the question says that it is from 001 to 006. So the z positions will be from 1 to 6. 1 to 6. So current is 5. R you have calculated it, which is 2, right? And dz is here, dz. Okay, over 4 pi. R you have calculated it, which is 2, plus z 3 over 2. Okay? This is what you have according to here. Okay, so you can input this one to the software. To the software. If you don't have Maple, you can use, for example, this one. You can use this one. This is symbolic. I think you have explored this thing before in the previous semester. So you can change this one to 6. So this is 10 4 pi. 10 4 pi 2 square. 2 square will be 4. 2 square will be 4. 4 plus z. Okay, so you can change this one to z. All right. So this one can be z. So you can calculate this thing. Oh, different answer. No different answer. I R. Oh, 3 over 2. Yes, 3 over 2. Oh, z square. Sorry. This one should be z square. See, you can get the answer 0.09976, which is same as the answer that we get. Okay, so this one is negative. Okay, angle is sorry, angle. The direction is this one. So negative 0.0999976 x directions. So you can use the software to solve this one. Okay, because your final examination will be objective question also, and you have to it's a online final examinations, so you can use calculator. Okay, you can use calculator, you can use software to help you to calculate all these things, simplify the steps. Okay, simplify the steps as long as you know how what is the step and what's the technique to be used. Okay, all right, so this is the second method. You get the same answer. Okay, so far any questions? No questions? If no questions, then we will move on to the next one. Now we look at this one. So we look at questions on page 109, which is this one. Example 2.2. Okay. So now you have a filament. Filament is actually a very thin wire, thin wire. Okay, with the length of 6 unit. Okay, you imagine you have a wire, thin wire. The length is 6 unit and is carrying 10 amperes of current. 10 amperes of currents. The current flow in the positive y directions, starting at 0 to 0. 0 to 0. Okay, so if let's say the question didn't give you any drawing, okay, so you have to understand the question and draw it out yourself. Draw it out the diagram yourself. Okay, mouse. Okay, so for the first one, you have to illustrate this column filament in a diagram. So you have to draw it out. So if this is your X, this is your Y, and this is your Z. Okay, so now your current is current filament is in flow in the Y direction starting at 0 to 0. Okay, if this is 2, this is 2. The length is 6 unit. Okay, the length is 6 unit. 6 unit. So it will stop at the position 8 lah, to make the length 6 unit. So this one is your current filaments. Okay, your current flow in these directions, positive y directions, and 10 ampere. 10 ampere. So you have complete the question 1. Okay, question 1 you complete. Determine the magnetic field intensity at point P061. 0, 6 might be here, 1 will be 1 unit here. So this is your observation point P, 061. that you wish to find out what is the magnetic field intensity, what is the H at this point. Okay, what is the H at this point? So we could use the formula that we have learned. Okay, I over 4 pi r cos alpha 2 minus cos alpha 1. Okay, so we'll try to settle terms one by one. So I has been given 10 ampere, 4 pi, no problem. Now is the R. How to find the R? Okay, so R is a point that is along the axis of the current filaments. Okay, so the line that join the P and the point T, okay, will have a 90 degrees angle form. Okay, this one, 90 degrees. So your point T is over here. So the coordinate of the point T, okay, you can determine it, okay, by referring to your current filaments. Your current filament is along the axis Y. So its X is 0, right? Y is X is 0, Z is also 0. But why you don't know? Why you don't know? So when you don't know the Y, you refer the Y coordinate of point P, which is 6. Okay, so now here you go. You got the coordinate T. Okay, coordinate T. So now we find what is the what is the vector R? Okay, what is the vector R? So it will be observation point 0, 6, 1 minus the point T, the position vector. Okay, look at my bracket. It is not round bracket. So I get 0, 0, 1. 0, 0, 1. Okay, which means that my magnitude will be equals to 1, because this is 1. And my unit vector R, it will be Z. It will be Z, because this one divide this one, you will get Z. Okay, so I have got the value for this. Okay, now let's move on to the alpha 2 and alpha 1. So I will join this together. So what do you think? Which point should be A? Which point should be B? Any ideas? This point should be A or B? A or B? Anyone?
Adding to.
Yes, very good. A, because it has smaller value, so this one will be B. Okay, so remember the one that attached with the smaller value will be alpha 1. So this one will be your alpha 1. Okay, alpha 1. You will take the outside angle. This one will be outside angle. If you draw this thing and redraw it, okay, just like this one, you redraw it. This is your y-axis, right? You redraw it. Okay, you redraw it. This is 2. Okay, so your observation point is, okay, Z over here. It is 1. This is, if you redraw it, this is 8. This is 2, 6, and 1. 6 and 1. So it will be here. So this one will be your alpha 1. This one will be your alpha 2. Okay, so it means that this one is your alpha 2. This is your observation point, point P. Yeah. Okay, so alpha 1 will take the outside one. Alpha 2 will take the inner one. Okay, just like this one. You don't take the outside one, right? Okay, if you refer here, you don't take the outside one. You take the inner one. Okay, so this is alpha 1 and alpha 2. Okay, so let's find what is the alpha 1 and alpha 2. So for the alpha 1, you can get it by refer to this triangle. Refer to this triangle. So let me draw it up. So this is basically your point P, right? This is point T. Okay, so this is your point A. So the value is 2, right? So for point T, the value is 6. Okay, which means that the length over here is 4. Yeah, the length over here is 4. And this is your alpha 1. And the length over here from T to P, you have calculated it is 1, supposing to be 1. So what will be your alpha 1? So maybe you need to find out what is this theta 1. Theta 1 you need to find out. Okay, so your tangent, maybe I will write in this way, 180 degrees minus sorry, minus alpha 1, okay, which is a theta 1, will be equals to opposite over adjacent. Okay, so this one actually represent the angle theta, theta 1, right, theta 1. So you can calculate what is your alpha 1. So tangent 1 over 4. So you get 165.96 degree. Okay, degree. Who cannot get this one? Alright, can So this is your alpha 1. So let's look at your alpha 2. See, your alpha 2, you can get it from here. There is a small triangle here, so I will draw it up. So this is your point B, this is your point T, this is your point P. Okay, so this is coordinate 6, this is coordinate 8. So obviously the length over here is 2. And the length over here is 1. And the length over here is 1. Okay, so alpha 2, where is your alpha 2? Okay, it's here. It's here. So you can use a tangent. Alpha 2 equals to opposite over adjacent. Okay, opposite over adjacent. So 26.57. Okay, 26.57. I think this is easy, right? You should be able to get it. Okay, so we have find the alpha 2. So this one, these two settle. Now left this one. The directions of the magnetic field. So it is equals to the directions of the current flowing cross product with the unit vector R. So for this case, you see, your current is flow in the positive Y directions. And your R is Z. Okay, R is Z. So this is positive Y and your R is Z. Yeah, R is Z. So if you're using this diagram, Y cross with the Z. Y cross with the Z, you will get X. positive x because you are following the direction of the arrows. Okay, so this one will be the directions of your magnetic field. So now the magnitude, you can calculate it. Okay, so for the I, 4 pi r cos alpha 2 minus cos alpha 1. This is the directions. Okay, so what is the I? I given is 10. Huh? I given is 10. So 4 pi r. Okay, r is 1 unit, right? And the cos alpha 2. Alpha 2 is 26.57 minus cos 165.96. 65.96. Okay, and the direction is x. We can straight away fill up x. So you can start calculate. So you get 1.48 x directions. Ampere per meter. Yes, thank you, Miklik, for your response. Okay, can you get this one? So this is, you get it by using method 1. Method 1. This one you get it by using method 1. Now I'm going to show you how to get the same answer by using method 2. Which is this one. IDL, right, cross product with the R over 4 pi R cube. This one is from here. Okay, from here. So this one, this you already know. Okay, is the directions of, it is the current and magnitude 10. So this one is the directions. Okay, the directions of the current. Okay, so for this case, the DL, okay, is equals to dz. Okay, because it's along the z-axis. Sorry, it's not along the z-axis. It's along the y-axis. Sorry, y-axis and in the y directions. Right? See, y-axis in the positive y directions. In the positive y directions. Okay, this one settled. How about this one? This one, okay, is equals to, you take the observation point 0, 6, 1 minus the source of the magnetic field. So the source of the magnetic field is lying along, okay, the axis y. So the x value is 0, z value is also 0. But for this method 2, you don't need to find out where is the t coordinate. You don't need to find out this one. Okay? You just put variable y over here. Because you are, it is along the axis y. Okay, so you don't need to find out what is the value. So it will be 0, 6 minus y, 1. 6 minus 1, 1. Okay, this is for the r over here. Okay, now we look at this one. Now you have the cross product, this and this. Okay, this one and this. It means that now DL cross product with the R. So it will be equals to dy, sorry, 0 dy, okay? This is y, right? Cross product is this thing, cross product. So don't worry, this is not complicated. If you still remember how to perform the cross product. So everything this one, actually you can use Maple to solve it also, but just want to show you the step. So this one will be 0 dy, right? 0, 0, 6 minus y, 1. Okay? So for the x, you cover this first column and first row. So you have a dy. This is 0, so you have an x. Okay? Minus, you see this 0, this is 0, so you don't have the y components. And for the z also, 0, 0, 0. So basically you just have this one. Okay? So this thing all has been simplified into dy. Okay, into dy. So let us write it out. This has become dy. Dy in the x directions over 4 pi, you see, r cubed. So just now you already get the r. So to find the magnitude, is equal to 6 minus y, you square it, plus 1, you square it, right? This one, it will be the magnitude. Okay? This you square it, this one you also square it. So you get this. Okay, now we put it here. 6 minus y square plus 1. And because this is square root and you have power 3, then it will become this. Okay, become this. Now this is a d hash. You want to know the hash. So you need to integrate I over 4 pi 6 minus y square plus 1, 3 over 2. And this is dy in the x directions. Okay, so the interval for the y, you can look at the length of your current filament, okay, from 2 to 8. Okay, so you just key it into your software. So this is y, right? 4 pi 6 minus y, so you have 6 minus y power 2 plus 1. Okay, and then here the I is 10, right? I is 10. Okay, so just 10. Okay, press. Oh yeah, this one you have to change because it is from 2 to 8. 2 to 8. Okay, you can get the answer 1.48. 1.48. So you can straight away 1.48 x directions ampere per meter. The same, right? 1.48. Okay. So this is the answer for method 2. So how many of you actually prefer method 2? Can you raise your hand? No one. How about method 1? Okay, thank you for your response. So it is your choice. I just want to show you that, okay, you can actually use different methods. They are actually all started from here. Okay, this one, this. Okay, so but when you are using this method, you no need to worry what if you assume the wrong angle. Okay, so you don't need to worry. So just use this one, you can get the same answer. Okay, so for the following calculation, I will just focus method 1. Okay, you can explore the method 2 yourself. So by the way, let's look at the directions of the magnetic field that we have determined, which is in the x direction, right? So you can actually use the your right hand. Okay, use your right hand. This is the where your current flow. Okay, so your point P is at the top of your current filaments. Okay, so when you use your fingers, okay, to show you the direction of the magnetic field, you can find that, okay, when you roll your four fingers, this is the directions of your thumbs. Okay, the other four finger will be going this way. Okay, so it will be like coming up from the page. Okay, when it is coming out from the page, the symbol is this one. So it is in the positive x directions. So this one actually is the same as what you have calculated. Okay, it's in the positive x directions. Okay, positive x direction. You use your finger, so this is your finger. Okay, so positive x direction. X is at the front, so it is pointing this way. Okay, so the symbol used is this one. Okay, symbol use is this one. Means that the magnetic field is coming out in this way and going up here. Come up. This is 2D, 2D. All right. Okay, we move on. So we move on with this. Maybe we can try it later on. Okay, we look at the magnetic field from an infinite current filament. Eh? Infinite current filament. So just like the electric field, you have a finite line. Okay, you have an infinite line. So when it is infinite current filaments, the equation will be simplified. So in this case, we will have two categories. The first one is semi-infinite line. Semi-infinite line, it means that you know, okay, the starting point, okay, maybe it's at a zero, okay, but you don't know when it stopped or it stopped at infinity. Okay, this is semi-infinite line. We have the second category, which is infinite line. Infinite line is it start from negative infinity and it ends at positive infinity. Okay, so for this case, okay, you can simplify the equations for the h, okay, by assuming the angles of alpha 2 and also the alpha 1. So this is point A. So this is point A, right? Point A. This is point B. Okay, so this is the point T that joining the observation point. Okay, this is 90 degrees. So this angle, okay, will be alpha 1, right? Alpha 1. So it is 90 degrees. Because this thing, okay, terminate at infinity. This is alpha 2. When it moves further away, this alpha 2 will become very smaller and smaller, and at the end, it is approximate to 0. Approximate to 0. So when you replace this 90 degrees over here and 0 over here, the whole equation can be simplified into this. And into this. While for the infinite line, okay, this is the same, okay, for your alpha 2. Okay, it will approximate to 0. But for your alpha 1, right, alpha 1 is this one. The angle over here, alpha 1. So when it moves further away, so the angle will become greater and greater and maximum at 180 degrees. Okay, so you can put this alpha 1 here and alpha 2, 0 over here. You can get another equations okay, for the H. And this equation is valid for infinite line. Okay, valid for infinite line. You can compare the difference. Okay, so here is over 4 and this is over 2. It's over 2. Okay, which means that this one is 1 over 2 of this one. And 1 over 2 of the infinite line. Okay, so we can look at example. Is there any example in your module? Let me check. Okay, you can go. This is what we have gone through just now. So there are more examples. Maybe we'll talk about it tomorrow, or you can read it yourself. Okay, so this is what I have mentioned for the semi-infinite and finite line. Is it the same? 1, 2, 3. Yeah, it's the same. Let's look at this one. Example 2.5. So you have an infinite current line of 3 ampere. Okay, 3 ampere infinite. You can see the symbol. This is towards the positive infinity. This is from the negative infinity. Okay, and the current is flowing in the positive x directions. So find the magnetic field H at this point. 1, 2, 3. Okay, 1, 2, 3. Okay, 1, 2, 3. So what is the equations that you have to use? What is the equation that you have to use? So because it is an infinite line, so you have to use this one. Okay, so the things that you have to find out actually not much because you have eliminated the alpha 1 and also the alpha 2. Okay, so let's see here. It's okay, I think. So the equation is H is equals to I over 2 pi R, right? And this 2 pi R, this, yes, this one. So I has been given 3 ampere. Okay, so you just need to find out R over here and also the directions of the magnetic field. Okay, so this is your observation point. You need to find out what is the vector R. Okay, you need to locate where is point T. Okay, where is point T? And this point T, we are very sure that it is along the current filaments, which is along the x-axis. Okay, so for the point T, the y value, okay, y value is equal to 0, and the z value is also equal to 0, right? You are very sure. All the points along the x-axis will have a coordinate y0 and also the z is 0. Okay, so this is something we don't know. So when we don't know the coordinate of the x, we have to refer to the observation point, which is 1. So it is 1. So this one will be equals to 1, 2, 3 minus 1, 0, 0. Okay, so it will be equals to 0, 2, 3. Okay, so this is the distance vector between the point P and also the point T. Yeah? Okay, so the magnitude, okay, it will be equals to 2 square plus 3 square, right? Okay, so we can find this is 4 plus 9 square root 13. Yeah? Okay, square root 13. Okay, so we need to find out this one also. Okay, so this one will be equal to 0, 2, 3. Okay, divide with square root 13. Okay, meaning that this is 2 over square root 13 y, okay, plus 3 over square root 13 z. Okay, so this is the unit vector r. Okay, you have to take note this unit vector r is different a bit compared to the previous two questions, because you see here you have two components, y and also the z. Okay, so here you will have y and z component. Okay, okay, so you have settled this one. Let's look at this one. This one showing the directions of the magnetic field. Okay, why not you try to tell me before you calculate this thing, right? Why not you try to tell me what is the directions of the oh no, this one you cannot, because it has two directions. It's okay. So we go to this one. So this one will be the cross product between the length and also the R. Okay, so this one, the current filament is flow in the positive x directions. So you have positive x. Okay, and cross product with this. Okay, you have to take the whole thing. Okay, you take the whole thing. Right. So how to do it? So x will cross product with the y. So let's see. X cross product with the y. As cross product with the y, you get z. So the value remain, nothing, no changes on the value. Okay, you get z plus as cross product with the z. As cross product with the z, you get negative y. Okay, because you are in the different directions, so it is negative y. As cross with the z, you get negative y because in the reverse directions. Yeah, reverse direction. So now you got this thing, so you put it here into your answer, which is 3 ampere over 2 pi r. So the r is square root 13, right? Square root 13. And this is the unit vector phi that you got. So it is combinations of z direction and also the y directions. It's 3, right? 3 ampere. Okay, so you can simplify it. So you have 0.07 z, okay, minus 0.11 y amperes per meter. Is it correct? Three. Okay, something like that. Let's try one more. Which is this one. Okay, so for this question is for the semi-infinite current filaments. So it begin at 0, 6, 0. Okay, you see this is your axis y. So it begin actually here and extend to negative infinity. And extend to negative infinity. So if it carries 4 amperes of current, find the magnetic field at this point. Magnetic field at this point. So for this one, okay, even though you have an equation for this semi-infinite line, right? But this one is based on the assumption when the current filament is in these positions, okay, which means that when the alpha 1 is equal to 90 degrees, then you will get this thing. But obviously for this one, right? So the alpha 1 is not equal to 90 degrees. Okay, which means that you need to find out what is alpha 1 and replace into the formulas for the magnetic field, this one. Okay, but what you can uh, uh, approximate is the angles for the alpha 2 because it is extend to negative infinity. So for your alpha 2, okay, it will be equals to 0, and this is for sure. Okay, so we look at this case. So still we have to start from here. H equals to I 4 pi r, okay, cos square minus cos alpha 2 alpha 1, okay, this one. Okay, we still have to start from here, okay, but here we are sure that this alpha 2 is approximate to 0. Okay, so I we know 4 amperes, so we have to go for the r over here. Okay, so before we find the r, okay, we need to know what is the t, right? So the t is over here. So the t will be along this y-axis, same like the current filaments. Okay, so that, okay, your x is 0, okay, y you don't know, and the z is also 0. So for the y, you will be following the y over here, okay, which is 8. Okay, so the r will be negative 2, 8, 1 minus 0, 8, 0. Okay, position vector p minus position vector t. Okay, and this is equals to negative 2, 0, 1. Okay, this is your distance vector. And for the magnitude, okay, it is equals to negative 2 square plus 1 square, right? So it's equals to square root 5. Okay, while for your unit vector r, okay, is equals to this. Okay, negative 2 over square root 5. Okay, this is x plus 1 over square root 5, and this is z. Okay, so you got your unit vector r. Okay, unit vector r you got already. Okay, so what is next? Okay, alpha 1. Alpha 1 is your next. So alpha 1 is over here. Okay, if you look at this triangle, this point, connect this point, and connect this point, you have a triangles. You can see, can you see it? This triangle. This is 90 degrees. Okay, so we're going to draw this thing out. This is point P, this is point T, and this is the point B. Okay. This one should be point. This one should be point B, right? Point B should be alpha 1. This one should be alpha 1, right? Alpha 2, right? This one should be point B. Okay, I think there is a mistake over here. The alpha 1 should be here, right? This one should be point A because it has smaller value. Point B should be here. Okay? So when you're joining them together, this one should be your alpha 1. And this one should be your alpha 2. Right? Should be your alpha 2. So this one should be your alpha 2. Should be alpha 2. Oops. Alpha 2. Alpha 2. Okay, alpha 2 it should be here. So this is the distance between point P and point B. You can refer here, which is square root 5. And this point is, hold on, let me check again. Begin at this point. Because this one begin at this point. Mm-mm. This one, is it the same as here? Let me check this one. Okay, sorry. So this one, yeah, is correct because it begin here. So this one should be point A, this one should be point B. Yeah. So we actually should follow the flow of the current. So this one should be point A. Yeah, it's correct. This one should be point A, and this one should be point B. Okay, because the current is flow in these directions. Current flow in these directions. Okay, so this one I erase. So this one will be your alpha 1. Alpha 1. Okay, and the distance from here to here is, this is 6, this is 8, so the distance is 2. The distance is 2. So the tangent alpha 1 is equals to opposite over adjacent. Opposite over adjacent. Opposite over adjacent. Okay, 48.19. 48.19. Okay, so we can form to this one. Oops. Okay, which is to calculate the directions of the magnetic field. Okay, so the direction of the current flow cross product with the R. Okay, so current is flow in the negative y directions. Okay, negative y direction, you see, in these directions, negative y. Okay, and cross product with the r. This is -2. -2 over square root 5 x plus 1 over square root 5 z. Okay, so again we have to use this diagram. Okay, negative negative will give you positive. So numbers stay. Yx, yx. So it gives you negative z because in the reverse directions, yx. Okay, plus you have a negative here, so it becomes negative yz. So yz give you positive x. Positive x. Okay, so you can put it here. 4 ampere over 4 pi square root 5, and this is cos 0, the alpha 2. Alpha 2 is 0. Okay, alpha 2 is 0. Okay, alpha 2 is 0. Okay, minus cos 48.19. Okay, and multiply with this one. Negative 2 over 5, square root 5. Z minus 1 over 5 x. Okay, so this thing you can cancel it. So you have a negative cos 0 minus cos 0.042 z. Okay, minus 0.042 x ampere per meter. Okay, ampere per meter. No. How come same? Let me calculate again. Cos 0 minus cos 48.19. Yeah, this is 2, 1. This is 2, 1. Is this the answer? Okay. So just now I made a mistake for this. Please take notes. So the A and B actually depends on the direction of the current flow. So in this case, current flow in this direction. So this point will be A and this point will be B. So just like here, okay, because the current flow in these directions. So this is A and this is B. Okay, it's not about the value which one is smaller. Okay, like this one also, like this one no. Okay, because this one current flow in this direction, so this is A and this is B. Okay, let me check again. Yeah, for this one also. All right, so A and B, it depends on the direction of the currents. Currents will flow from point A to point B. Point A to point B. Okay. So this is the final answer for these questions. Any questions so far? Okay, so before I end the lectures, let me go through again what we have learned today. So today we have learned about magnetostatic, which is generated by beside the magnet bar. It can be also generated from the flow of DC currents. Okay, when the current flow, there will be magnetic field generated surround it. Okay, so it depends on the shape of the wire. When it is straight line, so the current will flow in these directions. But when you make the wire in the form of loop, okay, it will become solenoid. So some sort like it will become a magnet bar. You have a north pole and also the south pole. Okay, and our earth itself is also a big magnet. Okay, so today we'll be covering two laws in this chapter, that is the Biot-Savart's law and also the Ampere's law, for us to calculate the magnetic field at a certain positions. Okay, so this one I think you know. Okay, so this one, I think this one is the wrong symbol one. This one is a wrong symbol. It should be a vector R. Later I will correct it. Vector R, this is 2 and this is correct. Later I will correct this thing. Okay, so this is the Biot-Savart's law. It states that, okay, the magnetic field intensity is proportional to the currents. So if you have a bigger or greater currents, you will have greater magnetic field. And if the distance, okay, is greater, okay, the distance between the observation point and also the current filament is larger, you will have a smaller magnetic field. Okay, so this one is the generally what the Biot-Savart law says. Okay, so you can determine the directions of the magnetic field by using your right hand rules. So the thumb will be pointing in the direction of the current flow, while the other four fingers will show the directions of the magnetic field. Okay, so when the symbol is this, okay, it's a cross, it shows that the magnetic field is in. Okay, going in. Okay, going in the page. Okay, when the magnetic field, when the symbol is a dot, it shows that the magnetic field is coming out from the page. You just imagine you have a, if you have a page. Okay, if a page, this is a page, right? It's a planar. So if the magnetic field is coming out means that it is from bottom, okay, towards up. Then this one will be a dot. But when it is going in, okay, going in the surface, going in the page, or going in the planar, then it will be cross. Okay, it will be cross. So this is the formulas for us to calculate the magnetic field from a finite current element, current filament, by using the Biot-Savart's law. So basically, you can just use this one. Okay, and if you're interested, you can also use this one. It depends on you. Okay, right. So now for this part, you'll be dealing a lot with the cross product between the x, y, and also the z. So this is how you determine the cross product between terms. Okay, so if they are following the direction of the arrows, then the directions will be positive. If they are opposed or in the reverse directions of the arrows, then it will be negative. Okay, and one more thing. Okay, so the AB will be depend on the direction of the current flows. Current will flow from point A to point B. Okay, and alpha 2 attached to point B, alpha 1 attached to the point A. Okay, point A. Okay, same like the previous chapter, you also need to find out where is the T. Okay, because before you can figure out what is the R. Okay, so I think that's all for today.